Welcome to our video on injective functions featuring October the cat. So she's actually not going to be very useful in this video. So injective functions is what we're going to talk about, and it should sound like another word that you've heard before. So hopefully it sounds a little like surjective. And they're related kind of in a sense, but kind of not. So let's just do a little review, right? What does surjective mean? A function's surjective if it's onto. So that means its codomain is the same as the range, or another way to think about that is the image of the domain is the codomain. So we're going to introduce a new definition over here for injective functions. So let's define a function f. Let's say it has a domain A and a codomain B. So that's going to be one-to-one And you might be saying, Jason, I learned what a one-to-one function is a long time ago. I thought you were teaching me something new. Well, oh, wait. Hold on, that is... Wait a minute. I have the wrong definitions in my notes. Anyway, whew. I thought you'd be teaching something new. This isn't new. Well, you're right. It's not. Injective functions. Right, again, we sometimes write this one-to-one like this. Whew. That's just another definition for injective. Just like surjective functions can also be said onto, injective functions are also said as one-to-one. So if you've talked about one-to-one functions before in a traditional math class, then this will be the same thing. We're just generalizing it to a larger framework, right? A more abstract framework. These don't have to be real numbers. These can be any kind of sets. They could be strings. They could be sets of sets. They could be sets of sets of sets of sets, right? Let's not go back to chapter 2 craziness, but it could be all those things. Okay, I'll finally finish the definition. Something is injective, it's one-to-one, if the following is the case. If two function values equaling each other implies, and I don't know if we've used this notation before, but I'm going to be very clear about it, implies that those x's must have been the same thing in the first place. So this is kind of a weird way of phrasing what, a lot of people have seen before and know kind of more intuitively. Many people are more familiar with the contrapositive. Now, you may have heard that in a logic class. We'll talk about it in our logic chapter later in this class. You may have heard the contrapositive. The contrapositive says, sorry, let's not use the if language here. The contrapositive says, if x1 is not the same as x2, then, again, you can also think of this as if then. So I guess you could write if here and then right here. That implies that the function values cannot be equal to each other. This first thing is used more often in proofs, I think, but we're not going to be doing not really doing proofs for injective and surjective functions. We're going to kind of gloss over that, and we'll do more about proofs again in a later chapter about proofs. So, contrapositive to a logical implication, like P implies Q is the regular, then not Q implies not P, and these are logically equivalent. Does that not make any sense? We're going to talk about it later. If it does make sense, that's great. Okay, so let us get going with a little picture. You may have seen this shape before. It's called a parabola. Is a parabola injective? No, it is not one-to-one. You may have heard of the horizontal line test. Well, it doesn't look like I've heard of horizontal lines from that diagram. You may have heard of the horizontal line test. The vertical line test is used to determine whether something's a function. The horizontal line test is used to determine whether something's one-to-one, aka injective. And that's what the definition is really saying, right? If we have two different inputs, they can't have the same output. That's what the contrapositive says right here. If we have two different inputs, they can't have the same output. So something like this is not injective. All right. So again, we're going to kind of be talking about these definitions in the terms of the functions that you all know and love, and then we're going to be playing with them a little bit more in the homework assignment for what they can look like in other situations, in more abstract situations, in less numerical situations. But I think numbers and graphs are kind of an easy way to introduce these concepts because it's very visual. All right. So let's do an example. Are these one-to-one, injective, and onto, or onto, I should say, surjective? Remember, this just means injective, and this just means surjective. Let's look at a few examples. The identity function. So you probably have seen the identity function. You may have heard the identity function called x, but we can identify it. We can create it more formally by writing the identity function I. Let's index it I sub a. It's the identity function for a given set. Goes from a domain, and the codomain of the identity function is always the domain. So it goes from a set to itself, which is not weird. Most functions in like a calculus class, go from one domain to like R to R or something like that, or maybe a subset of R to R. All right, and the rule here is just that you give me an input, the output is unchanged. All right, so that's what we've got here. Is this one-to-one? Is this onto? Think about this. Play with the definitions. And then we're also going to ask it for letter B, which is the constant function. How can we, and again, constant function, we've worked with constant functions. How can you write it with this more formal function notation? Well, let's call the constant function K or H, whatever you want to call it. K is usually for constants. Let's call it H. Let's call it constant function. H goes from A to A. It could be another set. It doesn't actually have to go to A. Say it goes from A to B. And h of x is some constant c. And c is some constant in the set B. Is this one-to-one? Is this one onto? So pause the video if you need some more time. Think about these and write down your answers, and then we'll go through it together. All right, so you should be saying, all right, the identity function, if this is the real numbers, it's just a line y equals x. And yeah, it's going to be injective. It's going to be surjective. But another way of thinking about this is without this. So injective, look at the definition. Let's do this without a graph. If two values are equal to each other, if their function values are equal, then their input values must have been equal. That's the definition of injective. Well, that's exactly what we have here, right? If two function values, like we can look at this, right? Right? If f of x1 equals f of x2, well, f of x1 is x1. That's what this exactly means. So this right here is literally the definition of injective. So we know this one's injective. And similarly, we know it has to be surjective as well. How do we do that without a graph? For something to be a function, everything in the domain must be covered. For something to be a function, everything in the domain has to have a function value. Well, here, the domain is the codomain, and the inputs are the outputs. So yeah, everything in the codomain must be covered. We know it's surjective. So you can do this with graphs, but really, it's good practice to start thinking about these more abstractly. because that's what we're working with here. We're moving away from numbers again. I feel like, that's the joke about algebra, but now we're really moving away from numbers. All right. And the constant function, right? Again, graphically, you've seen it graphed like this or something before. And hopefully your answer was maybe, because we don't actually know. It depends on the sets. So, if A has more than one thing in it, if our domain is more than just one element, then it's not injective. Right? Everything's going to the same place. If your domain is more than one number, you're going to fail the horizontal line test. It's injective if every output has a unique input. That's another way of phrasing this, right? If every output, I don't know how to spell output. Gosh, that was bad. If every output has a unique input, I should have just erased it. I did much better on input. Okay. So that's just another way of thinking of injective. And that's certainly not the case unless our domain is really, really small. So who knows? And then what about surjective? Well, again, it depends. If B, it depends on how big our codomain is, right? If our codomain is just C, the element containing C, then it is. But if it's more than one number, so if the size of our codomain is more than one, then it's not surjective either. But otherwise, it could be. Let me know if you have questions about that. All right, we're going to finish this video with, we're going to have a little fun. All right. Maybe it's fun for me. I don't know if it's fun for you. Use calculus, our favorite tool, to prove that f of x, I mentioned we're not doing many proofs, but there's something cool we can do with something like this, is injective. Remember, injective means that every output has a unique input. It means horizontal line test. It means if two outputs are the same, that means their inputs must have been the same. It means if two inputs are different, their outputs must also be different. Lots of ways that we can think about injective, aka one-to-one. But one of the ways that we can do it is by looking at the derivative. Now, the derivative of this function, you could write this as an exponent of 1/2. You could use the power rule with the chain rule. You're going to get that the derivative is this. And here's something cool that you can do. Remember, if the derivative's positive, the function's increasing. If the derivative's negative, the function's decreasing. If the derivative ever equals 0, it's flat right there. This is always a positive number. This is positive for all x in the domain. And the domain will be all, the domain of this function is all x at least 2. So that means f is always increasing. It's never constant. So if you have a function that's always going up, and again, this is a square root function, move to the right 2 units. If you have a function that's always going up, it must be injective. If you have a function that's only increasing, it will never have duplicate outputs because it's always getting bigger. It's never going down and it's never staying flat. Always must have. So can never have duplicate outputs. And again, this isn't a super formal proof. We're going to talk about formal proofs later on in this class, but just a little fun, a little surprise, a little, hey, here's some calculus. Everyone loves calculus, right? Let me know if you have any questions, and that's it for this video. Remember, injective is just what you've done before. It just means one-to-one. We're just taking it to the abstract.